Hello friends, welcome back. I am Anurag Srivastav and I am working as an assistant professor in instrumentation department of College of Agriculture, Engineering and Technology under Indira Gandhi Krishi Vishwavidyalaya, Raipur, Chhattisgarh. In the previous lecture, we have studied the anatomy and physiology of various systems of human body. In this lecture, we will discuss about types of biomedical sensors that can be used for capturing biomedical signals. In this lecture, we will cover different types of biosensors like biopotential electrodes, physical sensors, gas sensors and optical sensors. Their construction, principle and working will be discussed in this lecture. Now, first of all, we have to see the basic difference between sensors and transducers. Sensors is a device which can sense the changes in their surroundings into electrical form. The changes can be in the form of change in temperature or change in concentration of gas or in some other form. Sensor converts these changes in its surroundings into measurable electrical output. Sensor will respond to the change in physical quantity, but not able to convert it in other form. One of the example is thermistor. It is a sensor which can sense the temperature and produce electrical output, but not able to convert energy in other form. Whereas transducer is a device which converts one form of energy into other form. Not all transducers are sensors, but most of the sensors are transducers. The example of transducer is LVDT, that is linear variable differential transformer, that converts motion or displacement into electrical form. A biosensor is a device that converts biological, physical or chemical response into its equivalent measurable electrical signal. Types of biopotential sensors include physical sensors, gas sensors, optical sensors, bioanalytical sensors and others. Now, coming to the biopotential sensors, it senses and converts ionic current or potential produced inside the body into measurable electrical signal. These ionic potential measured by electrodes, which provides interface between body and electronic instruments. Types of biopotential sensors include invasive and non-invasive electrodes. Invasive electrodes involves penetration of needle-shaped electrode through the skin for measurement of ionic potential. It is mostly used to record and study signals from a specific zone of the brain like electroencephalogram EEG signal or muscles like EMG, that is electromyogram, which can be further analyzed for surgical procedures. These electrodes were surgically implanted inside the scalp or muscle fiber for better localization. Non-invasive electrodes does not able to provide accurate information as they are placed on the surface as electric potential produced by neurons becomes weak with distance. It is made up of stainless steel or platinum. It can be configured as a strip when arranged in columns and as a grid when arranged in both rows and columns. Invasive electrodes are mostly used for monitoring patients suffering from epilepsy and other mental and muscular disorders. In this section, we will study about the non-invasive electrodes and its types. These electrodes measure the potential generated inside the body from skin surface and therefore much safer as compared to invasive type. It can be used for recording signals from brain, heart and muscles. The signals can be recorded are EEG signal, ECG signal, that is electrocardiogram signal, and EMG signals. These electrodes are safer as compared to invasive electrodes, but has to suffer disadvantage of lower amplitude as compared to invasive electrodes. There are basically 4 types of non-invasive electrodes. They are wet electrodes, MEMS electrodes called as micro electromechanical system electrodes, non-contacted electrodes or capacitive electrodes, and surface contact or dry electrodes. Now, firstly, we will discuss about the wet electrodes. The most commonly used wet electrodes for recording of biopotential signal is silver chloride electrode. These electrode is connected to the skin via electrolyte gel, which reduces skin electrode impedance, thus providing better conductivity. The equivalent circuit for the wet electrodes are shown in figure. In the figure, you can see that the electrode is placed at topmost layer of the skin called epidermis, which we have discussed in previous lecture. The electrode is connected to the layer via gel. Now, coming to the MEMS electrodes called as micro electromechanical system electrode. It is a form of dry electrode, consists of micro needle made up of metals or polymers. These electrodes penetrates through the outermost layer of the epidermis called stratum corneum and therefore does not harms active cells and tissue. The advantage of using these circuits are reduced impedance caused by outermost layer of a skin, and as these electrodes are fixed, it reduces motion artifacts. Now, we will discuss about surface contact dry electrodes. These electrodes directly connected to the skin without gel and needles. The impedance is much higher as compared to needle type electrodes. It provides great comfort to the patients as compared to other two described earlier. Due to presence of hair, the recording can be unstable. Therefore, a special spring-like structure is required to push and hold electrode to the skin. And finally, we discuss about non-contacted or capacitive electrodes. These electrodes are not connected to skin via gel or needles. The coupling to the skin can be provided via insulator like air, clothing, etc., and can be represented by capacitor, which is connected to the skin surface. It consists of metal plate made up of copper and active circuit elements on PCB, that is printed circuit board. Because it is basically a non-contact type electrode, it provides comfort to the patients. The major disadvantage of capacitive electrodes are motion artifacts, as these electrodes cannot be fixed completely. Now, the electrode placement for measuring ECG and EEG signals is shown in figure. For ECG signals, these electrodes measures polarization and depolarization of heart and muscle cells. Standard 12 LED system for ECG recording is shown in figure. Apart from 12 LED system, 3 and 5 LED system can also be used, but not able to reveal crucial information. For EEG, 10-20 electrode system is shown in figure. The number 10 and 20 refers to the distance between adjacent electrodes, which are either 10% or 20% of the total distance from front to back or right to left of the skull. The total distance is based on the anatomical location on the scalp, nasion and inion. EEG signals can be recorded using single electrode or more than 100 electrodes. The selection depends on the requirement and amount of information we want to capture. In this section, we will study about the physical sensors. Physical sensors are used to measure physical variables like temperature, pressure, flow, force, displacement, radiation, etc. In biomedical field, physical sensors can be used to measure physical quantity such as blood pressure, blood flow, body temperature, bone displacement, medical imaging, etc. The physical sensors can be used for real-time monitoring, like in robotics, wearable electronics, etc. Type of physical sensors that we will study in this section are thermal sensor. These sensors are used to measure body temperature. Examples of thermal sensors are resistance temperature detector RTD, thermistors and IR infrared sensors that we will discuss in this section. Next is magnetic sensor that can be used for flow measurement, and mechanical sensors that can be used to measure physical quantity like blood pressure, weight, force and displacement. Now, coming to the thermal sensors. Firstly, we will discuss about RTD, that is resistance temperature detector. It measures temperature by measuring changes in resistance of metal wire. The widely used metals for RTD are copper, nickel and platinum. These metals has positive temperature coefficient of resistance. The positive temperature coefficient means the resistance of element increases with temperature, while the negative temperature coefficient or NTC, the value of resistance get decreased with increase in temperature. Temperature measurement in case of platinum ranges from minus 200 degree centigrade to plus 650 degree centigrade. For nickel, minus 80 to plus 260 degree centigrade, and for copper, minus 200 to 260 degree centigrade. Typical resistance of metals at 0 degree centigrade for platinum are 100 ohms, for nickel 120 ohms, and for copper around 9 ohms. Out of the above three metals, platinum has excellent corrosion resistance and copper has highest temperature versus resistance linearity. RTD found in three configurations: wire wound RTD, coiled element RTD, and thin film RTD. Now, coming to the next thermal sensor, which is thermistor. It is combination of thermal and resistor. Like RTD, it is a resistance thermometer which measure temperature by measuring change in the resistance. Thermistors are available with materials having negative temperature coefficient as well as positive temperature coefficient. General purpose thermistors having temperature range of minus 80 degree centigrade to plus 300 degree centigrade. Thermistors are made up of oxides of metal such as copper, cobalt, manganese, etc. It is available as disc type, bead and glass encapsulated. Its response is faster as compared to RTD, but has exponential temperature versus resistance response. Apart from measuring body temperature, it can also be used for measuring blood flow by placing two thermistors at known distance and measuring temperature difference between two thermistors. Now, coming to non-contact type temperature sensors. In this section, we will study about infrared thermometer, which are popular nowadays. It measures the temperature by detecting amount of infrared radiations emitted by the object. It is based on the fact that IR radiations or infrared radiations emitted from all objects which are not at absolute zero temperature. These IR radiations are proportional to the body temperature. IR thermometer focuses IR radiations coming from body onto the sensor called thermopile, which converts IR radiation to heat and then in the form of voltage. This voltage is directly proportional to the body temperature. IR thermometer measures temperature ranging from minus 60 degree centigrade to about 1400 degree centigrade. Now, in this section, we will study about electromagnetic flow sensors. The electromagnetic flow sensor is based on the principle of electromagnetic induction, that when electric conductor moves through the magnetic field, it induces voltage EMF across the conductor. According to Faraday's law, the expression is given by E is equal to BLV, where B is equal to magnetic flux density, L is equal to length of the conductor or diameter of the pipe, and V is equal to velocity of the fluid or conductor. For measurement of liquid, a non-conducting pipe is placed in a magnetic field produced by the coil. Two electrodes are flushed into the non-conducting pipe opposite to each other. When liquid flows, EMF is generated across the electrodes and proportional to the velocity of liquid. In this section, we will study various displacement sensors used for measurement of displacement, pressure, force and other physical quantity. A displacement transducer is an device used to convert motion of an object into equivalent electromagnetic, magnetoelectric or electrostatic signals. The motion can be linear or rotary. Displacement sensors can be used for measurement of other physical parameters. They can be converted in the form of displacement. Force, pressure are the physical parameters that can be measured using this. There are basically three types of displacement transducer: resistive transducer, capacitive transducer and inductive transducer. Now, coming to the resistive transducer, it is based on the fact that change in the resistance is directly proportional to the length of the resistive element and inversely proportional to the area. The relation is given by the expression R is equal to rho L by A, where R is equal to resistance in ohms or resistivity of conductor, A is equal to area of cross section, A is equal to cross sectional area of conductor in a square meter and L is equal to length of the conductor in a square meter. There are various types of resistive transducers such as potentiometer, strain gauge, RTD resistance temperature detector and thermistor. Now, the next transducer in the category is potentiometer. The potentiometer can be used for measurement of linear and angular movement. The figure shows measurement of linear displacement through potentiometer. The input voltage is applied and the output voltage is measured across fixed and sliding terminal. The output voltage is taken across resistance R2 using Ohm's law equation V is equal to I into R. The sliding terminal moves and the resistance across the output terminal changes and therefore output voltage also changes. You can see in the figure that when the slider of potentiometer moves toward A, then the value of R2 resistance will be increased and therefore output voltage also get increased. If slider of potentiometer moves towards B, then the value of resistance R2 will get reduced and so the output voltage. Thus, by measuring the output voltage, we can identify the amount and direction of movement. The next transducer is strain gauge. Strain gauge is a transducer basically used for measurement of force, pressure, weight and displacement. The resistance and resistivity of conductor varies due to deformation in shape because of strain which results from applied force, pressure or weight. The strain can be compressive or tensile. Due to compressive strain, conductor become shorter and broader, and because of tensile strain, the conductor becomes longer and narrower. Because the change in resistance is very small, the conducting wire or a strip were arranged in zigzag pattern fixed on a non-conducting material. This arrangement ensures the small change in resistance can be measured with high accuracy. There are two types of strain gauge, unbonded and bonded. In unbonded strain gauge, the strain gauge is not directly bonded to the surface which is subjected to the stress or which is under study. whereas bonded strain gauge are directly placed or bonded on the surface of the device or component which is subjected to stress or which is under study. The strain gauge circuit is shown in figure. The strain gauge is connected to arm of the bridge circuit. The value of resistance R1, R2 and R3 are so selected to keep the bridge in balance condition. In balance state, the voltmeter shows reading of 0 volt. With application of a strain, the resistance of a strain gauge changes, leading bridge to get unbalanced. The voltmeter will now start to show the reading which is proportional to the applied strain. The figure shows the arrangement of measurement of blood pressure using unbonded strain gauge. In this arrangement, a diaphragm is coupled directly by an armature to movable frame that is inside the transducer. Blood in a peripheral vessel is coupled through a thin fluid filled catheter to a disposable dome that is sealed by the flexible diaphragm. Changes in blood pressure during the pumping action of the heart apply a force on the diaphragm that causes the movable frame to move from the resting position. This movement causes the strain gauge wires to stretch or compress, and in a result, the change in resistance that is proportional to the pulsatile blood pressure measured by the transducer. Now, in this section, we will discuss about the inductive transducer. The most popular inductive transducer for measurement of displacement, pressure, force, etc. is LVDT. It is based on the principle of mutual induction. The physical parameters to be measured has to be converted in the form of displacement. It consists of one primary winding and two secondary windings connected in series in such a way that output voltage V0 is equal to difference between induced voltage V1 minus V2. And soft iron core is placed in such a way that when core moves towards S1, that is left, then induced voltage is S1 greater than S2 and output voltage will be positive. When iron core moves toward S2, that is in right direction, then induced voltage is S2 greater than S1 and output voltage will be negative. At null position, induced voltage in S1 is equal to the induced voltage in S2, making the output voltage V0 is equal to 0. Therefore, by analyzing the output voltage, displacement can be measured. In displacement transducer, the last section is capacitive transducer. Capacitive transducer used for measurement of displacement, pressure, gas, force, etc. Capacitive transducer consists of two metal parallel plate separated by dielectric medium. One plate is movable while other plate remains fixed. Dielectric medium can be material, gas, liquid, etc. Value of capacitance is directly proportional to the overlapping area and inversely proportional to the distance between the plates as shown in equation. When distance between the plates due to displacement, pressure or force changes, then the value of capacitance will get reduced. Thus, we get the displacement get converted in the form of change in capacitance, which can be easily converted into electrical form. Now, in this section, we will discuss about the gas sensors. Gas sensors measures the concentration of gases like oxygen, carbon dioxide, etc. in the blood, therefore reflecting the effectiveness of the lungs. Gas sensor finds its application in ventilators, anesthesia machines, respiration monitor, etc. Oxygen concentration in fresh air is about 21%. When inhaled, only 5 to 8% of oxygen is absorbed by the lungs. Exhaled air contains around 13 to 16% of the oxygen. Oxygen saturation level SpO2 is one parameter to assess amount of oxyhemoglobin that is oxygen bounded hemoglobin present in the blood relative to total hemoglobin. The oxygen saturation for healthy human is around 95 to 100%. Apart from oxygen, various gas sensors can also be used for measuring carbon dioxide and pH level in the blood. Pulse oximeter is one of the most popular type of gas sensor used commercially. It is a non-invasive, cheap and convenient technique for measurement of SpO2 level. Blood consists of oxyhemoglobin and deoxyhemoglobin. It is based on the fact that each light is having different wavelength, red light having a wavelength of 650 nanometers, IR radiation 950 nanometers. Oxyhemoglobin absorbs more IR as compared to the red light, and deoxyhemoglobin absorb less IR and more red light. Pulse oximeter consists of light source LED and IR source at one end and photodetector on the other end. Finger is placed between source and detector. The ratio of received IR and red light is proportional to the oxygen saturation level in the blood. In this section, we will discuss about principle and working of optical biosensors. The optical biosensors produce a signal that is directly proportional to the concentration of analyte, example glucose. It is based on the principle that there is a change in optical property of light due to change in characteristic of biological medium, that is biorecognition elements or bioreceptors. The characteristics of biological medium that may be changed are absorbance, reflectance, scattering, fluorescence, polarization or refractive index that can be detected by optical sensors. There are mainly two components used in biosensors. First one is biological medium or biological recognition elements or bioreceptors. They are the molecules that attaches analytes on their surface, which in turn changes their optical properties, thus producing biosignals that can be passed on to the biosensors. Examples are enzymes, antibodies, antigens, cells, etc. And second one is optical transducer. It detects the reflected or refracted light coming from bioreceptors. Examples are interferometer, grating, SPR, that is surface plasmon resonance, etc. The figure shows complete setup of optical biosensor. The signal which we get from optical transducers are further amplified, processed, and the interpretation will be done accordingly. Now coming to the conclusion part. In this lecture, we have covered principle and working of various types of biosensors. We have started with invasive and non-invasive electrodes, and then we have seen various physical sensors, gas sensors and optical sensors. We have seen their application. The knowledge about this sensor can help for effective development of biomedical instrumentation in future. Thanks.